the orbital approximation, what we essentially have done is taken, when we express our wave function in that form as a product of spin orbitals, we're really assuming that electron-to-electron repulsion, we're pretty much ignoring electron-electron repulsion, okay? So fundamentally then, using products of hydrogenic orbitals is wrong. The form of the wave function is wrong because of that electron-electron repulsion term in your Hamiltonian. You can, however, try to account for electron-electron repulsion by, instead of using the actual Z, the actual charge of the nucleus, you make that an adjustable parameter for each of those orbitals, okay? So, because that takes into account the fact that each electron will not feel the full force of the nucleus because of the presence of the other electrons. And then you can use the variation method, okay? So you do a variational calculation to optimize the value of the Z. So you get what's called an effective nuclear charge. So here's a reference of some extensive work that's been done there. So in the case of helium, for example, for a one electron in the 1s orbital of helium, okay, you can get lower energies if you assume the effective nuclear charge that's affecting that electron to be 1.6875 instead of, what's Z for helium? Instead of Z equals 2, use an effective Z of 1.6875. Okay. For lithium, the effective nuclear charge is for an electron in the 1s is 2.69. What do you notice here? 1.69, 2.69. There's an effective screening of about 0.3, right? 2 minus 0.3 is 1.7, and then 3 minus 0.3 is 2.7. So effectively, the effect of the other electrons on an electron in the 1s orbital would be shielding of it by an amount equal to about 0.3. Shielding of the nuclear charge by an amount about 0.3. Okay? And the effective nuclear charge for an electron in the 2s orbital in the case of lithium would be 1.27. Okay? Let's see. Lithium has how many protons? Plus 3. So the nuclear charge is plus 3, right? And then you have 2 electrons in the 1s orbital, and then you have that electron in the 2s orbital. You have 1 electron there. You'll notice, okay, you might think, okay, there's 3 protons pulling in, right, and 2 electrons pushing out. You might say, shouldn't the effective nuclear charge be 1? Well, your electrons are not fully shielded. These 2 electrons in here are not fully shielding that outer electron from the nucleus because it's smeared out, right? It's not like they're always in between the the nucleus and the other electrons. So it's not going to be a full shielding of 2 electrons. So what's the effective shielding here? What's 3 minus 1.27? 3 minus 1.3. Let's see. 3 minus 1.3 is 1.7. So instead of being, so the shielding is not equivalent to just a full shielding of 2 electrons. The 2 electrons effectively shields only 1.7 by 1.7 instead of by 2.